So my name is Jose. Uh, so I'm very honored to be here today. Last year I was doing Camera, and today it's a big talk of 45 minutes, and the responsibility is big. So I had to select a fancy name for my talk, which is the delusive side of computational biology and the bad science behind bioinformatics. I had the choice to present my PhD data and results and master results in a dry way, meaning that I just present classically my results and my research. But I choose to take this opportunity to broadcast an issue which concerns me. It's about bioinformatics. Everybody is talking about bioinformatics, new science, good science, but the fact is bioinformatics is somehow it's dirty, it's nasty, it's hard to work with, and I want to present this aspect today. So, to start, sorry for
Oui. ملتيبليز لك على الدش بس شوي بليز خاطر تقصر طبعا عليك. Voilà.
So, why exactly I chose this topic? Well, because of what we call the lone bioinformaticians. And the term lone bioinformaticians is not necessarily bad. It's actually representative of a bioinformatician who's working in a wet lab, like me. I work at the development and biomolecular lab. So these kinds of computational scientists, computational biologists, we will see them more frequently, probably in the next years. These are different scientists from the bioinformaticians who work on bioinformatics lab. There's another philosophy, another concept of thinking, and actually, so I want to present this aspect for you today. So to present myself, I did my maîtrise in medical biotechnology at the Institut Supérieur de Biotechnologie de Monastir. My master's degree in SAP, and then my PhD at Faculty of Science of BZ with the supervision of Professor Dr. Najed Sarayabid. And if you are interested in my research, you can find me on my Google Scholar account or my ResearchGate account. So, why I choose those bioinformatics and computational biology? We have to differentiate between them. And to start, I just took this plot here. I tried to actually count the number of occurrences of two terms, bioinformatics and computational biology, on PubMed. And as you remark here, the two terms increases, the usage of the two terms increases during the late 90s and the start of the 21st century. And why is that exactly? This is not necessarily because bioinformatics appears at this period. In fact, unlike the classical thing, bioinformatics is not a recent science. Bioinformatics started since the 60s of the last century. So normally when Margaret they have started to collect the data for and creating the peer database for its project. But during the year 2000, there is the big impact of the human project genome. Okay, and then when it was submitted, everybody was interested to probe this genome. So they started to use bioinformatics tools. Okay? So what is exactly bioinformatics? I'm just working here from H2 unit course. It simply tells you that computational biology is the usage of bioinformatics tools to study biological issues. And the difference between computational biology and bioinformatics is that bioinformatics is actually the invention of new algorithms. Okay, well, this is mainly the difference between the two terms. But in this talk, I will use the two terms interchangeably. Okay. To make the things clear here, let's say these two gentlemen, Louis Pasteur and Camille Hachette. Now, Camille Hachette actually he is an instrumentalist who invented the microscope, and this microscope particularly was used by Louis Pasteur, which is a microbiologist. So let's say that Camille Hachette is a bioinformatician who invented an algorithm, and this algorithm was used by a computational biologist who's Louis Pasteur. So I started to work on the venomics, the term venomics. And actually venomics are, the venoms came from different organisms, like snake, scorpions, and spiders. And these tissues actually contains lots of interested biomolecules. These biomolecules can be active on different, for example, anti-channel blockers or anti-proliferation or anti-invasion. And there is lots of interesting activities there. So we have to, in order to study these peptides, the proteins contained in the venoms, we have to study the structure. And why exactly we have to study the structure? Because of what we say here, the central dogma of biology. The central dogma of biology actually tells us that probably the most interesting part in the cell is happening with the proteins. So to understand, you can name any mechanism, for example, the interaction of a hormone and the receptor, an antibody and an antigen, an enzyme and a substrate. So probably everything is happening at the level of the protein. There is some exceptions, but let's generalize this. So in order to study the proteins, well, we have to study their structure. And to solve the structure of the proteins, there are different techniques. Mainly the X-ray and NMR and Q electron microscopy. These are the experimental techniques. And there is a fourth technique, which is the structural prediction with modeling or molecular modeling. Now, for example, cryo-electron microscopy became now a very successful techniques. And last year, the Nobel Award on chemistry was awarded to scientists who increases the accuracy of this technique. Now, the electron microscopy is becoming accurate to the level that we can detect two objects distantly with 1.6 angstrom. The second or the last technique is purely theoretical. It's structural modeling, and we are going to talk about this technique in the next slides. So I started just to as a historical fact. So the laboratory of venoms and biomolecules at Pasteur Institute is actually working on the venoms of different animals. And Professor Majed Sarayabid was working on different toxins at that time, mainly the blockers of K-previous channels or potassium channels blockers. And she typically she used HPLC and tried to characterize these proteins structurally. And she used bioinformatics to study the structure activity relationship of these venoms. Now, she used also structural bioinformatics to probe the activity of these venoms, mainly in solving the NMR spectra of these peptides, and for example also to map the very interesting properties of the venoms, like the potential of electrostatic potential, or also the mapping of the antigenic group on the surface of the proteins. And typically she was using a very archaic workstation at that time. And compared to our Galaxy S3, for example, which is also deprecated hardware, this workstation is very limited in terms of computation, but it works at that time. And so, one day, she was wondering why we have actually a very big number of sequences, and these sequences are actually active on Cavi-1,3 potassium channel. The Cavi-1,3 potassium channel is actually highly expressed on lymphocyte helpers, and theoretically, if we can inhibit the Cavi-1,3 potassium channel, we can also inhibit the activity of these peptides, of these cells. And these cells are actually implicated in the autoimmune diseases like the nasty, for example, multiple sclerosis. So the idea here is to collect the data from these proteins, of these peptides, and then try to make a computational study and design a new peptide, which is highly active on Cavi-1,3 potassium channel, and then highly active also on highly selective for Cavi-1,3 potassium channel, because of the problem of selectivity toward Cavi-1,1 and Cavi-1,2 potassium channels, which are actually very homologous for the potassium channel. Now, we started to collect the data and the IC50s for the Cavi-1,3 and Cavi-1,1 potassium channel. And then we used software to make a predictive model in order to generate 18 billion sequences, mutative sequences. And these 18 billion mutative sequences were reduced to 265 sequences at the end. So, to study the activities of these sequences, we have to obtain a structural model of Cavi-1,3 and Cavi-1,1 potassium channel. So, and in order to get these structures, we actually have to model the proteins using a theoretical tool, which is homology modeling. The homology modeling actually consists on identifying a putative homologous protein, which structure is solved by either X-ray or NMR, and then try to build the model based on this template. So we have the target sequence, which is Cavi-1,1 and Cavi-1,3 potassium channel, and we have a template by which we are guiding our modeling procedure to build the 3D structure of the interested protein. So we have actually two choices. The first choice is to use an homologous protein from a bacteria. The second choice is to use another protein, which is highly, or the similarity of this protein toward Cavi-1,3 and Cavi-1,1 is high. And so we have these two choices. At the end, we selected the bacterial protein. And why is that exactly? Because, one problem. Okay. Because actually, we rely on, in bioinformatics, on databases. And databases actually contains a lot of anomalies. For example, if we choose to model our protein based on Cavi-1,2 potassium channel, that's because this sequence or this structure, the Cavi-1,2 potassium channel, contains an external loops which looks suspicious. Why is that? Because this geometry, if you observe the loops here, are actually highly exposed and highly symmetric, which is probably not the case. Okay? So probably this structure contains lots of errors. So because of this, we didn't select it. And actually, the databases of the structural database contains lots of other errors. For example, you can find a lot of confirmations. So if you have to select between one of them. The second thing, for example, missing coordinates, unrealistic geometries, and so on. Okay. The second, for example, example I gave here for an error inside the databases is the complex of a co-crystal between adenosine A to A and the most famous molecule in the world, which is the caffeine. So in this structure, actually, we try to observe here the position of the cafe inside the pocket. And when using X-ray crystallography, we actually don't see the molecule, but it's, let's say that it's shadow, which is the electron density matter. And so we have the error here consists of the swapping of the conformation of the caffeine. So the caffeine actually is not in a highly accurate position. It can swap. Okay? So this is actually an error inside the databases. The problem of the databases is that most of the people have a lot of confidence in the data. So before using the databases, you have to be very careful about your choice, even if it is a structure or a sequence or any other data. Okay, the second problem in bioinformatics, and this is what I call the unforgiven cell. Why the unforgiven cell? Because most of the people either if they are transition to bioinformatics career or actually also trying to use bioinformatics occasionally, they don't ask questions and they don't study their system. So the first thing to do in bioinformatics when you use computational tool is to know your system. This is very important. And it consists of going blindly computational without having any idea of what you are going to do and where you want to get exactly. Okay, so I learned this with the hard way. So now we have our 256 sequences, and we want to study their interaction on Kv1.1 and Kv1.3 potassium channel. But in order to select the most putative sequences, we have to know if exactly our docking score is reflecting the reality, which is the IC50. So we came up with this idea to collect different peptides, sequences from the databases, and use them as test cases or benchmark. And because we biologists, we like the simple linear regression, we try to do this on our profile. And we didn't really get it. The profile was so big. And I spent likely 2 months doing extensive experiments and simulations in order to improve this profile, but it didn't really improve. It was published in 1988, and I didn't read it at that time. And this paper suggests that when a toxin actually interacts with the channel, it's actually the protein is actually unstable when the potassium is present inside the toxin, the channel. Okay, so I had to remove these potassium ions from the structure in order to give realize the docking. And bingo. So I had a linear relationship between the IC50 and the docking score. Okay, so this is actually helped us after that to establish what we call here a cutoff score in order to select our sequences. And actually we were able to identify 5 interesting peptides, highly potent or highly active on Kv1.3 potassium channel, and also highly selective. The other case of this unforgiven scene is actually the kind of proteins, the PL2, the phospholipases. And this work was actually done by Duja Beiru and Iman Junaisa, which were under the supervision of Professor Nazira Marakshi. So the team actually purified 2 PL2. MVL-PLA2 and CC-PLA2. The first one actually the preference of the first one is to the neutral phospholipids, like phosphatidylcholine. The second one has a more preference to the negatively charged phospholipids like phosphatidylglycerol and serine. So in order to explain these results, we know that actually the interaction of the PLA2 with the membrane, which contains the liquids, is actually highly governed by the electrostatic forces. So you have your, for example, your protein and your membrane, and you have the PLA2 which is trying to go into a Brownian dynamic or motion inside the physiological media. And then when the electrostatic potentials start to interact, you have the actual. You have actually the interaction with the membrane. So we decided then to answer this question based on an electrostatic study. And so we calculated what we call here the dipolar moment for each one of these proteins. And we actually found that the CCPL2 contains, this, for example, the electrostatic charges in CCPL2, or the positive electrostatic charges, are actually highly present nearby the interaction surface of the protein with the membrane. Okay, but the electrostatic charges here are actually non-isotropic, so you don't have really a different electrostatic potential with MVL-PL. And so we explained the physiological results using this method. Okay. The other bad thing in bioinformatics is to use your tool before understanding it. And actually, bioinformatics is a double-edged sword. So you always get the results, not like biology. But it's up to you. It's up to you to decide either if these results are actually real results or they just rush. Okay? So, and I here give the example of the mighty Deinococcus durans bacteria. And this bacteria can actually withstand 500 grays of radiation. And let's compare it to the radiation for Hiroshima and Nagasaki, which is of an order of 5 to 10 grays when measured at the center of the mushroom. So this bacteria is actually very resistant to radiation. Dr. Qais Abdira and Dr. Haytham, they were studying this bacteria and tried to infer some genomics data and from the bibliography if there are exactly interesting systems that can explain this resistance. So Qais and Haytham actually have lots of genomic sequences, and they came to us and asked us, why don't you take a look and, for example, try to model these proteins and tell us if there are really a pattern to explain this resistance. And the sequences, we actually find a pattern inside a protein called SLPA, which is a surface protein of Deinococcus radiolurans. And we actually found that there is the folding of beta-barrel folding is frequent for these proteins with bacteria that are very resistant to the radiations. So actually we used here the not so accurate method to do this, because we tried to the accurate method, it didn't very get too well. But when we tried, let's say the 3D method, actually we were able to observe this folding. And so we know our tool here. If we didn't know the limitation of our tools, then we can't really infer these properties. Because even with low quality of model, you could actually get your model talk and get really interesting results. Okay, and this is very common issue also. Like bioinformatics work like magic. So most of the people actually suppose that I can use the software for every case I want to answer, or any question I want to answer. And this is very wrong, actually. But before proceeding, I like to present you the case of peptide, which is called CFTX, or chlorotoxin. And this chlorotoxin actually is a blocker of, supposed blocker of the chloride channels. And the CFTX actually is highly potent for the, it has an anti-invasion property. It has also an homologous protein which was purified in our lab by the team of Dr. Najib, and it shares 63% of identity with chlorotoxin. So we tried to study these two peptides and to explain why exactly they are capable of these pharmacological profiles. Okay. So the mechanism of cell invasion actually involves two sub-mechanisms. The first one, the cell had to shrink its volume in order to get to the narrow spaces in the extracellular matrix. Okay? And the second mechanism involves the degradation of the extracellular matrix molecules. So this, in order for the cell to ensure the invasion, it had to have these two proteins, actually. The first one is the CLC3 chloride channel, which is responsible of the cell volume shrinkage. The second one is the MMP2. So when we check the bibliography of the literature, we actually found a very discrepancy between the resources. Some papers describe the CLC3 as the sole target for the CLTX. Some others talked about MMP2. And so we decided to answer this question using computational tools. And so to do that, we started by establishing a 3D structure for the CLC3 channel. Now, normally, when you model a protein, you have to align your target with your target sequence, with your template. And the best tool, and by best I mean the most rigorous or the most mathematically rigorous tool, is to use the the dynamic programming software. Okay? So this software actually gave you the alignment, the best alignment from the point of view of a score, or the mathematically most optimized scores. So when you used actually these tools, we got to this model, which is very bad model. Why is that? Because you have these sort of anomalies in the secondary structures of the transmembrane domain. Okay? So this solution, this bad solution here, was obtained using the optimized tool. Okay? It turns out that when we combine our modeling procedure to the prediction of the transmembrane domains inside the target sequence, we get a much better model. So normally, if you use the evident choice, you are not going to get to a good model. But you have to adapt your situation, not for the software, but you adapt your situation to your case, to your specific case. Okay? So the second example I want to give about this issue. So here we started to implement a pipeline. We started, for example, we have a FASTQ file, say FASTQ file, and these RNA-seq actually were obtained from the genomes of scorpions. And we want to get from the FASTQ file to predicting the sequences and the structures of the antimicrobial peptides. Okay? And to do this, actually, the evident choice, or the most popular choice, is to use classical ORF predictions tools. But in our specific case, these tools ignore any peptide or protein which length is less than 100 amino acid. So we propose here another strategy, which is to predict the potency of the antimicrobial peptide using actually the prediction, the chemical-physical prediction of the ORFs. So this is also another example on how you should not go one solution for everything, okay, or one software for every issue you have to solve. Okay, and actually a question you should not ask to a bioinformatician, and also a lot of the bioinformaticians have to ask is which software to use in bioinformatics. We should not ask this question. Why is this? Because when you count, for example, the tools or bioinformatics tools which were published in the most 3 cited journals in computational biology, we have nearly 4,000 software or database or a server, and in 2018 alone we have 120 solutions. So you have lots of choices, and these choices are accessible, openware, and free. So you have to adapt your needs, not based on your system, and not adapting your system to based on what other people used or the evident choice and so on. Okay. The other issue in bioinformatics is the benchmark problem. The benchmark problem is actually consists of when bioinformatics tools are published, they are published in peer-reviewing papers, okay? And they try to show the best thing for these tools. So you have always the accuracy is high, the sensitivity is high, and everything is perfect. The problem is that when the authors try to evaluate their tools, they don't really evaluate these tools in a generic way. So they specifically choose only the systems for which they have the best results. Okay? But, for example, there's lots of experiments. For example, CASP or Capri and database experiment, they try to successively evaluate the performance of the homology modeling tool, the protein-protein docking tools, and the multiple sequence alignment software. The most valuable conclusion they actually obtain is that really there is no best solution for everything. And like this wise guy said, the only one golden rule is that there are no golden rules. This is exactly that when you have a software, for example, and you're studying an antigen system, you can apply it to this system, but not apply it on the, for example, metalloproteinases inhibitors. Okay, so the transferability of the algorithm is actually not working so well in bioinformatics, and so you have to benchmark your tools based on your specific system each time you're working on something. Okay, and in our case, actually, we have the, for example, we studied the MMP2 interaction with CLTX and ACTX peptides, and the MMP2 actually is composed of different domains, but we didn't really use all these structure to model our system. So I introduced some modifications. One of them is to remove the propeptide and the PX domain, but the most radical modification is to model what we call here the zinc cluster and structural zinc cluster and the catalytic zinc cluster. We actually have 2 representations of these zinc clusters. So we have the choice to represent this zinc as a sphere with plus 2 electrostatic charge. Okay, and also we have the other choice to what we to model the zinc clusters with what we call the bonding model. Okay, and this is actually the most accurate model. So when we made our radical modifications, we actually have to evaluate their validity. And so we established a long pipeline of validation using differing tools. So these are actually the tools we used for studying the interaction of the scorpion peptides with MMP2. And each time we have to evaluate these tools and establish curves. Okay, this took a lot of time, a lot of efforts, and this is really really not so trivial for some systems. So this is a very limitation in bioinformatics tool is that you have to benchmark and to test your system or your tool based on your specific case you're trying to solve. Okay, the dilemma score here is actually in bioinformatics. We rely on different scores. One of them, for example, is, let's say that you have two proteins, two conformations, and we can actually use software to measure the energy of these proteins. So for example, when you have a protein X and you measure the energy you obtain, for example, an energy of minus 1,000 kilojoule per mole. This is actually not the real energy. Why is this? Because the scores in bioinformatics are highly approximate. And I give the results here of measuring the distance between two atoms. Okay? So when you measure two atoms, the distance between two atoms in a crystal structure, you have a deterministic measure. It means that, for example, between A and B, you have 2 angstroms. Okay? But when you measure the distance in bioinformatics, you say that it's probably 2 angstroms, but it's up to you to choose if it is highly confident or not. Okay? So this is very approximate. And this problem actually can be manifested also when using the docking. So for example, for docking, you have 2 complexes and you try to measure the docking score between these 2 complexes. One is -10 and the other one is -9. And so you say that -10 is better than -9. And so I choose the first complex. This is also not so trivial. And when we encountered this problem, we studied the CRTX interaction with MMP2 and with ACTX. We actually made the docking for this protein, and we found that there are actually 2 putative sites. The first one is situated on the catalytic domain, and the second one is situated on the collagen binding domain. Okay, so we were unable really to get highly confident results because actually we can't really say that the pose or the docking solution with the minimum of score is the best solution. Okay, so we have to add other measurements. Okay, and this one, for example, measures the enrichment of the collagen binding poses for the highly ranked poses. Okay, and for CRTX MMP2, you have a single pose here, which is high distance from the other docking solutions, and we select this pose to represent the solution of the interaction mode of neurotoxin with MMP2. But for AACTX, you have a very close poses in terms of energy, and so we couldn't decide which one to take. Okay, so we are going to answer the question at the end of the talk, how exactly we proceed to select the pose of AACTX with MMP2. The other issue in bioinformatics here is the usage of the service. Now in bioinformatics there is 2 philosophies. when you use the software, so either you install the software on your machine, probably this software will be implemented on Unix, and the second choice is to use the servers. So actually this is two representation of a software which affect the pairwise alignment between two proteins. So in the first figure we have what we call the command line, okay, and the second one you manipulate the program on the server. The server actually, when developed, the server are meant to help non-experimental bioinformaticians to get their result quickly and fast. Okay, so the problem with this server is that it becomes a bad habit now to operate these tools in a black box. Okay, so a biologist, for example, he just take his protein sequence, he cut and paste his sequence inside the field, and he just run the analysis. Okay, but without really considering the specificity of its protein, without really considering the changing, optimizing the parameters. Okay, and the typical example I gave here is the usage of the 3D homology modeling servers, like IDAS or like Swiss model. Okay. So, for example, when you have a protein with two domains, okay, most of the people will take all the sequence and they just cut it and paste inside the server, and they get something like this, because servers cannot really, if you don't have really an homologous protein which contains all the structure of the template, so you're not going really to get to highly accurate results. Okay, so the first model is highly distorted and very bad, but the second one is actually much better because we used manual tools to model the protein. Okay, so servers beware when you use the servers. Never go black box at all. Okay, the other bad thing in bioinformatics, and this topic is always cited by many scientists, is that you have always to confirm your results, your computational results. You have also always to validate your results by experiments. But the problem is that this is not achievable for all the systems in bioinformatics. And here I gave, for example, the case of using the molecular dynamics to study the motion of the system. Molecular dynamics actually is one of the few techniques that allowed us to see what happens for the protein at the atomic level, and using also a time scale measure. So for example, it consists actually on getting your structure, 3D structure, putting the water, putting the ions, adjusting the temperature and for example the pressure, giving some velocity to the atoms, and see if the system is going to run to the stable state or unstable state. Okay, so we use this technique to do lots of things, measuring, for example, in thermodynamics properties or geometrical properties like distances between residues, hydrogen bonds, anything. Okay, and we use molecular dynamics actually to answer a question: is that why chlorotoxin is more or highly potent on MMP2? There is a phenylalanine at position 6, and this phenylalanine actually can be in two states, which we call a rotary state. And we found that for when the phenylalanine adapts the first state, it's more actually the protein, the interaction with metalloproteinases will be much better.
And when it adapts the second rotamer, the interaction becomes weaker. Okay? And so we studied the frequency of adopting these two conformations using molecular dynamics, and we found that when for CLTX you have an histidine at position 11, okay? So this histidine actually is not so constrained like protein, which exists for ACDX, because protein can actually introduce geometric constraints and influence the conformation of phenylate. And we were able to get to this level using molecular dynamics techniques, and we can really validate these results using any other methods or experimental methods. Okay. That's big. Get this one also, and get to the most important slide in this talk, is that why exactly, or when actually we have bioinformatics results, the most precious tool to analyze your results is not the code, it's not the algorithm, it's actually your inventory course of biology, of chemistry, of physics. That's all. Because actually, biology is the common language between experimentalists and computational biologists. And if you ignore this, you will get to nowhere. Simple as that. Okay? And this attitude now to ignore any sort of biology for bioinformatics, because there are some computational biologists, they say, I have just my code, I have just my computer, and I can do anything. This is not going to get you to anywhere. Okay? And, okay. This actually allowed us to answer the question of what or which docking solution we are going to select for AACTX. And the tool or the thing that allowed us to do this is simple evolutionary biology. So we asked the question actually, if we can't really decide using the energy of the docking score or the energy of interaction scores, we might use evolution. So if we remember that between CLTX and ACTX you have 63% of identity. And these peptides are actually homologous. So if CLTX is capable of interacting with MMP2 with X way or geometry, and if this geometry actually exists between the highest ranked poses with AACTX, then we can say probably for sure that the interaction mode between the two peptides are actually conserved. And we actually did this using the matrix of LMSD, and we found that the best solution for CLTX is actually very similar to the highly score, or the highest or the best solutions of docking for AACTX. And there it is. This is the interaction mode established by our study. It tells you that the CLTX actually interact with, not with the catalytic domain, but with the collagen binding domain. And thanks to this model, we were able to build peptide 2, peptidomimetic, which, to our surprise, did not inhibit the MMP2 activity, but actually it enhances it. Okay? Okay. But this final question is that, are we actually doing real science using bioinformatics? Yes, but you have to be vigilant when using bioinformatics. And actually when you're dealing, it's very easy to lie when you are a bioinformatic, when you are a computational biologist. So if you are a biologist and you're dealing with a bioinformatician, ask him to explain to you the biological issue. if you are a bioinformatician, you should actually not ignoring the. When you are a bioinformatician, you should not ignore the biological side of the system. And at the end of the day, we are doing modeling when we're dealing with model cell or the in vitro models and the cell, for example, the cell line models. At the end of the day, either bioinformaticians or biologists are modeling something. And this is the end. And so this is actually, I think, everyone who contributed this work, namely Professor Najed, who supervised my PhD and my master work, Sir Mohammed Al-Aib, Professor Najih Al-Marakshi, Hazem, Shihab, Husema, Ayub, Wasim, the research team at the Institute Pasteur of Paris, Dr. Hatem Sghair, Qais, Fatima Emel, Yashrif Al-Hamda, for sharing their opinions on this topic, and thank you, CDC organizers. You did a good job.